Okay, so let's get started. Welcome everyone. So I will have a brief recap. So last time we covered the basics of decoding on QEC. It's usually a classical method to analyze syndrome measurements that we can infer the probable errors and correct them. For example, the maximum likelihood decoding. And we know that the MLD is not the optimal approach. So today, Tobias will continue the second part of the decoding that to introduce more specific topics of different decoding models here. So it's your time, Toby. Thank you. Uh, sorry, maybe you can unmute yourself. We cannot hear you.
Okay, can you hear me now?
Yeah, okay,
Perfect.
go
All right,
ahead.
thank you so much. All right. Yes, so for the second part, I will talk about more advanced topics, as already said, more advanced topic of quantum error correction. So I put like a very short recap, so we just kind of remember what we did last time. It's already been a week ago. Yes, so as you know, quantum error correction deals with kind of protecting quantum information, and the idea is basically that we have some kind of logic information, let's say a qubit, and since there's noise that tries to attack our qubits, we need to somehow save it from the environment and from the noise that tries to attack it. And that's we do by taking our logic qubit and putting it into many physical qubits. Let's say the service code. And the nice part is now basically that now, since we have many physical qubits and we spread out the logic information over all these physical qubits, the logic qubit is now kind of redundantly encoded into many objects. And the nice thing of a coherent is, let's say of distance d, is that even if you lose a bunch of those physical qubits, the logic information is still preserved. It's still there. Of course, let's say if there's some noise or some kind of qubit loss, right, then the code is now a bit damaged. But there's some way to fix the code in a way that the code comes back to its original form and the logic information is preserved with a high probability. And the key part is basically you need to somehow find this correction operation that basically fixes your code. And this can be usually done up to d minus 1/2 errors. So if you have code of distance d, you can fix d minus 1/2 errors. And decoding is this process of finding the correction operator. And this is basically the usual process of how you do stuff. You have your logical state, you encode it into some connection code, then there's some noise that basically tries to damage it, and then you fix it using your decoder. And back, you end up hopefully with your original state row. And last time we basically learned with a very basic example how this decoding actually works in practice. And we looked at the 3-qubit repetition code as this basic example that pretty much encapsulates the most of what you actually need to know to understand what is actually decoding. And what we basically learned is that basically when we have our code, let's say we have our 3-qubit repetition code, which has some kind of code states, basically logic information is encoded as 0, 0 and 1, 1, 1 physical qubits. So one logic qubit goes into 3 physical qubits. Then if some error has happened, then we can decode it using syndrome measurements, right? Because in the quantum error correction codes, you're not allowed to measure the error directly. Instead, you have to measure syndromes. So kind of information, like you have to do certain measurements that basically do not touch the logical state, but give you kind of circumstantial information, what actually is going on, what kind of errors happened. And last time we, for example, learned that if an X error happened, let's say on the first qubit, then your initial state, let's say the 0, 0 state, which represents logical 0, is transformed into 1, 1, 1, 0, 0. So it's now basically not a code, it's not a code word anymore, because now we have this one here. So and using a syndrome measurement, let's we do these two syndrome measurement, which is like some kind of parity checks. The syndrome that you measure will basically tell you something has happened. I mean, we get now this one here. The syndrome will be a 1, 0, where basically 1 indicates that something has happened here. And when you now do decoding, you basically plug in your syndrome, then the decoder will then find the most likely error that has happened that matches this syndrome condition. That's basically the step as a parity check, which is, for example, this error here, which says basically an error on the first qubit and no error on the second, third qubits. And now to correct, you simply apply the inverse of the error, which is just applying the error again, which fixes you back to your code. Now, of course, the issue is, the main key crux of decoding is that the syndromes kind of give only circumstantial information, but they're not unique. Given a syndrome, there's many possible errors that could have happened. For example, in this simple case, for this syndrome, we could have this error here, but there's another error that matches the syndrome, which is particularly an error on the second and third qubit. So the error vector will be like 0, 1, 1. This error has the same syndrome, also 1, 0, but it's a weight 2 error, like there's 2 errors that's happened. So the maximum likelihood decoder will not catch this error because it will think this syndrome is because the most likely error is this one. So higher weight errors, let's say we have an error on the second, third qubits. For this error, the correction operation would tell you, okay, the most likely error is actually an error on the first qubit. So when you then apply the corresponding correction operation, this would look like basically x2, x3 from the error plus x1 from the correction. This will basically transform your 0 logical state that you actually had into the 1 logical state. Basically, you get a flip where there's actually not supposed to be a flip. Right, because basically initially you were supposed to be in 0 logical state, but after the error and your wrong correction, you end up in the 1 logical state. So then this means you have made a logical error, which is bad. So the key message is that when you do error correction, we can only, with absolute certainty, correct errors of weight d minus 1/2. So let's say if a distance d code, we can only correct errors up to d minus 1/2 errors. In this particular case, because this is a distance 3 code for x errors, we end up with only up to correction of up to weight 1 errors. So if a weight 1 error happens, we can fix it. If a weight error 2 or 3 happens, then it's over. Like we can't fix it anymore because we don't know what the correction operation is. Okay, so what does this imply? So this leads to some very interesting observation. I mean, let's say we have a generic NKD code, n qubits, k logicals, and distance d. And as I said before, we can reliably correct up to d minus 1/2 errors, because if you have this many errors, then our syndrome measurements will basically correctly the most likely error is always the one that that satisfies this condition. And but you can ask the question now, is this enough? Okay, let's take a very basic example. Let's say our favorite code is usually, if you ask most theorists and experimentalists, they will say the service code is probably the most convenient code for many reasons. So most experimentalists, they use the service code nowadays. Now the service code is the rotated service code actually is a d squared 1 d code. So basically it has d squared physics qubits, 1 logical, and d distance d. Now assume, let's say we have a single qubit error, right? Like let's say every qubit is affected by
Sorry, Toby, we cannot hear you. Or maybe it's due to the connection here.
Yeah, somehow, Toby, like, can you hear us? Can you?
It's kind of offline.
Hey, Toby. We cannot hear you.
Yeah, sorry, there's some issue with my tablet. So give me a second while I fix it. Sorry. Okay, back. Okay, so where did I lose everyone? What was the last thing you heard before the connection dropped? Sorry for that.
Yeah, maybe you can start with this slide 4.
Okay,
Yeah.
sorry. Yeah. Yeah, there was some connection issue on my tablet. So my computer is fine. We have the video, but the tablet lost the connection. But now we're back. So let's recap. Okay, so if you have an error, NKD error correction code, so that particular code, where it has in physical qubits, k logicals, and distance d, and we can correct up to d minus 1/2 errors reliably, right? But you can ask the question, is this actually enough? A good example is, let's say, the surface code. The surface code has d square physical qubits, 1 logical, and distance d. We learned about this before. In particular, this is the rotated surface code. Now let's assume every physical qubit is subject to 1 single qubit error with probability p, right, which is a reasonable noise model. We just assume that every single qubit independently can experience some error with some probability p. And now if you do the math, we can now compute the average number of errors that we expect on our qubit in our system. So as we know, the error probability is p per qubit, and we have d square qubits, right? The number of errors on average will be p times d square. Now, you can obviously see now this is much larger than the distance, right, of the code, which gives us the number of qubits of errors we can correct. So in other words, as we scale up our code, let's say our service code, the number of errors will grow much faster than the code distance. So meaning we get more and more errors, but the capabilities to reliably correct errors actually doesn't grow as fast. Meaning if we look at simply these numbers here, then it seems that basically as we scale up, we have a problem here. Okay, that seems bad on the first glance, but what we must consider, of course, the distance is the Hamming rate distance. It's kind of a worst case condition. Basically, we can correct any error of any form up to d minus 1/2 errors of any form. So this could be also very highly correct error in a very intricate pattern. But this is something very unlikely, right? So basically, usually errors don't have this highly correlated pattern, and this worst case is actually very conservative. So while we can only correct up to d minus 1/2 qubits, this assumes that the errors have a very particular form, that you would probably never encounter in experiment. And usual errors don't have this highly correlated form. They have often we can make some assumption that these errors have less complicated structure. Usually people assume that the errors are uncorrelated. For example, the errors are a simple tensor product of single qubit channels. So basically each qubit basically is independently affected by some error, and basically there's no correlation between neighboring qubits, let's say, for example. Each error is independent of the other. And basically one can show that in this case, assuming the errors are uncorrelated, we can get an exponential suppression for low errors below something called a threshold. Meaning if we have this condition and the errors is low enough, then we find that the probability to get a logic error, to get one of these nasty bit flips, decays exponentially with the code distance. All right. So here, basically, in this limit, we don't really have to care much about this Hamming rate condition. Instead, this distance condition. And here, for this, we have now a different paradigm where we have basically this kind of threshold behavior. Now, you can think of case, is this actually something real? Well, this was demonstrated in experiment. So in an experiment performed by Google, which was published this year, they basically studied the surface code for different code distances. So they had like a distance 3 surface code, distance 5 surface code, and distance 7 surface code, right? And they scale up the system. And then basically they basically computed the usual syndrome instructions and so forth in the decoding, and basically computed the logic error against the code distance that they expect. And what they basically observe is then if they plot the logical error against code distance, they find basically with increasing distance, the code goes down. And there's a log plot, and you find a line, means the code down, the error goes down exponentially, pretty much in the form as we expect here, the expansion of the code distance. And in fact, what they find is basically that the error suppression has a factor of 2. So if I increase the code distance by 2, let's say go from distance 3 to distance 5, the logical error increases by a factor of 1/2. And the same if I go from code distance 5 to code distance 7, again, the logical error halves. So you can easily see if this trend holds, as you scale up further, the logical error will go down exponentially, if this is the case. So I mean, you make the system bigger and bigger, and the error will go down more and more. Yeah, so this is the threshold that has been observed in experiment, but you can also study this in theory. And so this is something as example on the next slide. Yes, what I will show you is just some study we did. So I will just give you an example from work we recently did, where we looked at some threshold of a particular decoder. What the type of decoders I will explain in a minute. For now, I will just basically just show you that this is something you can observe also in numerically, for example, in just by simulations. Basically, what you can do is you can basically simulate, let's say, some code. In this case, we simulate the color code. We assume a certain error probability. So every qubit was suspect to some probability. Then we do the whole syndrome measurement and the decoding. And then we basically plot the logical error against the physical error. And we do this then for different code distances. Let's say for code distance 30, 25, and 37. So these are different graphs, the blue, orange, and green curve. And what you observe is something now very curiously. I mean, let's say we have code distance 13, right, a relatively low distance. You get the blue curve, right? And you see basically the error as the logical error decreases. Sorry, as the physical error decreases, also the logical error decreases. That makes sense, right? Less physical error, less logical error. Okay, you get some line. Now you can do the same line, but now with a different distance. Let's say distance 25. And you see again the same behavior, but you see the shape of the curve looks different. In particular, you observe something very curious. The same trend. Let's say go distance 37. You see that basically above a certain value of physical error, let's say about 0.15, you see that with code distance, the error increases actually. So as the distance increases, you get more logical error. So this is actually bad, right? Like you make the system, the code bigger and bigger, and the error gets worse and worse, right? But the funny part is if you go below this line here, below a certain error, you observe the opposite. You observe as the distance increases, you go from this 30 to 25 to 37, the logical error actually decreases, right? So you make the system bigger and bigger, and the error goes down. So this is exactly the behavior what we're looking for, and the behavior also that was observed in experiment. Now, where this transition basically from basically bad behavior to good behavior, this is called the code threshold. And at the code threshold, basically you see that all the different curves for different distances meet. They meet all at the same point. They kind of have a crossing here, basically where you go from bad behavior to good behavior. So this is called the threshold, and you can basically show that for many codes, this behavior continues, even as increased distance more and more. And you can see also a very nice feature. For example, you can make the curves collapse with a simple rescaling of the logical of the physical errors. You can see that all the different curves for all different distance, although they look very different, they can be made to collapse onto a single nice curve here. This is shown here. The second thing you can see is that basically you can now play this game for different codes and different types of decoders, and you can get different behaviors. For example, if I will talk about in a minute what this is, but there's a code called maxat decoder. You get a threshold at, let's say, 0.1. This corresponds to about 15%. But let's say if you use a different decoder called BPOSD, you get the crossing point happens, let's say, at 13.23% physical error rate. Generally, it means higher threshold means better, right? So if the percentage is larger, let's say 15%, this means you can tolerate more errors, right? So the higher this number, the better. So it means basically depending on the decoder used, you get different thresholds. Similarly, also for different codes, you get different thresholds. Let's say for a Tori code, you find the threshold is, let's say, 15.5, whereas for the color code, it's 15.2. The Tori code has a better threshold behavior, meaning it can tolerate more errors up to a certain percentage. So basically what it means is that if you're below threshold, then scaling up the code distance will suppress errors. Assuming these errors have, let's say, of a certain character, let's say they're uncorrelated. Of course, we know this is not generically true. Yeah. And yeah, so the point is, it depends on the code and decoder used. We'll talk about this in a minute. Also, it depends on the type of noise model. So these plots I showed here is for a very simple noise model. We assume only the data cube is subject to errors, whereas the syndrome measurements are noise-free. So for this, you get, let's say, a threshold of, for total code, let's say, a service code of 15.5%, 15.5%, yeah, relatively high. And but let's say if you use a different noise model, let's say like you assume circuit level noise. We talked about this in the last line. Basically, we assume that all the errors, that we actually implement the physical gates and assume every gate has some kind of realistic noise, and also the measurements are noisy and so forth. Then the threshold will actually decrease, right? Because now you have more noise sources, everything becomes way more complicated. But you can still show that for example, the service code has a threshold even under this full circuit level noise model. And usually people find error rates, threshold levels on the order of 0.1 to 1%. And yeah, so basically if you have errors below that, then basically you observe this exponential decay on errors, as for example has been shown in the experiment. So it means the experiment has a noise model, a noise which is lower than the corresponding threshold. Okay, good. Just a short mention that there's something you can of course also go beyond uncorrelated errors, because it's this assumption basically that all errors are singular and it's actually true in practice. I mean, it seems to be true up to at least to some degree, because we see this exponential decay of the errors. But this has been studied also by Google in experiment. Basically they plotted the code distance against the logical error, and they found basically this exponential decay, right? Because this is a log plot. So basically they found like a linear decrease, which corresponds to exponential decay, which is nice. So this is what you expect below threshold. But at some point, if they see some different behavior, there's some kind of plateau behavior where basically this exponential decay levels off. Instead, you get like a kind of a converged plateau. The error doesn't decrease any further, the logical error. And these are believed to originate from kind of correlated noise events with very low probability. So they happen like with 10 to the power minus 10 probability, probably caused by cosmic rays that appear with very low probability. So it means there, at some point, your noise model may change and may get more complicated. There can be other noise effects that come to play once your distance large enough and all the errors are brought down enough. Then new noise models can appear that are more complicated to solve. And this has important implications. For example, it has been mentioned that quantum computing is best done permanently shallow craters on the moon. This has been mentioned on a certain social media platform by a certain person. And but given that basically on the moon there's a lot of cosmic rays and a lot of cosmic events that can happen because there's no atmosphere, this is probably not a good idea, at least with super-lucky qubits. So there's a nice lesson we can draw from these experiments, how to perform quantum computing. Basically, you have to shield your system from the cosmic rays as much as possible. Also, something to consider, but I'm not going to talk about this. This is something I'm interested personally, together with Keisha and Arvind and Nikhil from Power and DAX, of course. We basically study the case where the noise is kind of adversarial. So basically, there's some kind of the noise is not caused by some cosmic events or by nature, right? By kind of random forces of nature, but actually there's some bad guy that tries to attack your system, right? So there could be, think of some kind of bad influence that basically specifically tries to induce noise in a way that it basically causes as much damage as possible. And for these scenarios, you could have to think of different ways how to combat noise. But there's methods, let's say, there's methods like list decoding and cryptography. You can apply it basically to solve that. But this is another interesting topic. So basically, my point is you have to think always about the noise model. And depending on that, you have to choose your code and how you basically decode things. Okay. Okay, now I will come actually to the key part that I think people are most interested in, basically, how do we actually decode stuff in practice? And the key part in decoding is, of course, need an algorithm that decodes your system. Then this, of course, we have to, because, as I mentioned earlier, the syndrome measurements give us incomplete information, and we have to solve an optimization problem in order to get to figure out what, given the syndrome, what is the error that has happened with high probability. And as I mentioned in last talk, decoding is an NP-hard problem, so it's very difficult. So therefore, if you actually want to solve it, you always have to make approximations, because if you want to solve the full problem, you will take too much time. So you need to make some kind of approximations. This implies there's an intrinsic trade-off, speed versus accuracy. If you want to be very accurate, you just solve the NP-hard problem or even the sharply hard problem if you prove the full problem just exactly. But that means you need to invest exponential amount of time. So meaning in this cases, the runtime will be high, but of course also the accuracy will be high. If you basically just brute force the full problem. Now you can start making approximations, right? And if you approximate a problem, it probably will become easier, but also at the same time, your accuracy will suffer. So there's now different types of decoders that basically now one or the other, like basically will be now run faster because you made approximations to your decoding problem, but also of course the accuracy will suffer. And over the time, people invented a lot of different types of decoders, and there's now a huge zoo of different decoders that basically play on this trade-off between accuracy and speed. And yes, besides that, also there's other things to consider. If you then really go deep into experiments, you have to think about basically how to implement it. Is there like good physical hardware that maybe is more suited to one type of decoder than the other? And also you need to think about basically what is really the hard limit on the runtime, because maybe depending on the setup, basically what's the clock speed of your syndrome measurements, right? How fast you need to correct syndromes. You need to be very fast. Let's say superhuman treatment is a very relatively fast system where basically all operations happen on a very fast time scale. Therefore, you need to go faster. But let's say if you have ion traps or ripback atoms, they have a slower processing time. So maybe then you can take more times to decode. So these are all the things you have to basically consider when think what is the best decoder for your quantum error correction setup. Okay, for next steps, I will now talk about a bunch of different types of decoders that people have proposed over times. There are way too many, so I will not be able to cover all of them. But I will just talk about the most important ones. First, just a short recap. I will just basically mention the full decoding problem. I will mention the full decoding problem as originally proposed. I think I already talked this wasn't last time, but let me just talk about this again, just as a brief introduction. So we have, and the decoding problem, we measure our syndromes, right? You know already the study. Then we want to figure out what is the corresponding error that's happened. And we do this by basically measuring the parity check matrix, which is a matrix that encodes your syndrome measurements. And then we find the most likely error that matches the given syndrome. And as I mentioned before, the syndrome condition is not unique. So therefore, we need to optimize. And what we optimize over is basically the error probabilities of all possible errors. So basically, we have now every error happens with a certain probability, which you can compute. And then we find the most likely error, basically find the error configuration that is most likely given the syndrome conditions. So now we need to solve this optimization problem in some way. So there's now many decoders I mentioned before, and I will start with basically one decoder that I personally worked on. They're called Maxa decoder, which was first proposed by the group of Jens Eisert. And where you basically just take the decoding problem and you map it onto an optimization problem. And particularly, you map it onto a optimization problem, which is called the MAXSAT. MAXSAT, or maximum satisfiability, basically is a well-used optimization method, which is used, let's say, for many problems in, let's say, logistics and finance and so forth. The basic idea is that in MAXSAT you find configurations of a Boolean variable E that satisfies constraints on each of the variables. And for example, and maybe to explain, I'll just give you a basic example. Let's say we have, this would be, let's say, a MAXSAT involving 3 different configurations, using for 2 variables, E1 and E2. And this basically, this would be basically the equation that basically defines your constraint. And basically what this is basically, this one is an OR symbol, whereas the other one, this is an AND. basically this asks, and we demand basically this must be true. Right? So it must be this Boolean variables, this Boolean condition must resolve to 1. Then this is satisfied. And we say this is good. And if it's not satisfied, then this solution is not allowed. So this is basically, you can see a way of encoding all syndrome constraints. For example, in this particular configuration, we basically say that E1 or E2 must be true, right? Because there's an OR constraint. And then we say on top, this equation must be true, which says that E1 or the inverse of E2. Inverse means basically take we flip 0 to 1 and vice versa. And the third condition is basically saying that the inverse of E1 or E2 must be true. And you now play this game and basically check all the possible values for E1 and E2. And if you now go through this equation, you can basically see the only one that satisfies all 3 equations at the same time is E1 equals E1 to be E1 and E2 being equals to 1. You can see this very easily because let's say if E1 is 1 and E2 is 1, then this condition is satisfied. Secondly, this condition will be also satisfied because E1 is 1 and this is 0, but that's fine. This is an OR statement. And find the same here. And you can check similarly that all other variables are not allowed. Let's say if E1 is 0, then one of these 3 equations will fail. So using this, basically, this Maxa basically gives you a way to basically input constraints on the variable, right? In particular on errors. And now one can show that each syndrome condition can be mapped onto such Boolean constraints of a Maxat. And there's now a prescription how you can do it. You can just run a certain algorithm. The basic is that basically each syndrome measurement, each syndrome can be basically represented as basically this as a Boolean parity check, Boolean addition. And you can now basically having basically have all these crazy syndrome checks. Basically, you basically do all these parity checks between the elements of the parity check matrix and the corresponding errors, which gives you like a kind of a long list of Boolean additions. And then you can basically take this one, but this one itself is in a bad form. So what you do is you break this down, this constraint down of the syndrome into 3 body terms, because this is a more animal form Maxat. And this you can do by introducing some kind of slack variables. You can basically break down this big syndrome condition into many connected 3-body conditions. And then finally, once you have it in this form, you still have this Boolean addition here. But this one, there's like a prescription how to map Boolean addition into Maxat constraints. So that involves 3 terms, as we've seen earlier. So any of these conditions here can be then mapped onto a Maxat problem by using these kind of prescriptions here that you can write out. So if you do this, basically you can map each syndrome constraint into a Maxat condition. And then afterwards you can just solve it. Basically, once you map it into Maxat, there's like a solvers that you can just download. They exist on people that use solve Maxam all the time. So they're very good solvers you can just use, and they will just solve the problem for you. So once you've written in this form. And the nice thing about Maxa is it's a quite accurate solver because it basically solves very close to the optimal solution, to the optimal problem formulation, but then it also makes it relatively slow. We'll talk about this in a minute about this trade-off. Another method I would like to talk about is belief propagation, which is a very popular method that is heavily used in classical error correction. So the idea in belief regression on the nutshell is basically you have some kind of basically you have the probability of observing a particular error given a syndrome constraint, right? So you have a given syndrome, and now we have then the corresponding probability of observing a particular error. And we want to maximize over all possible errors that match basically this condition. This is the decoding problem. But I mean, solving this, as we know, is difficult. So belief propagation approximates this by instead saying, okay, let's try to find the marginal probability for each particular variable, right? So we have each error, E1, E2, or 3 up to En for each error. Now we're trying to find the marginal probability. So the marginal probability of observing an error. And this is pretty much just the summation over this kind of full probability distribution, where we basically set the ith error to 1, and then we sum over all possible errors, right? So this gives us now the marginal probability. It says the probability of observing the ith error in the 1 state, basically being 1. Basically the probability of observing the ith error in one independently of all the other errors, right? So these are the marginal probabilities. Now, belief propagation is now an algorithm that computes such marginals in a local manner. And the idea is that basically you have to write down the decoding graph. So our parity check matrix, you can basically think of this being some kind of having some kind of graph structure. And the belief propagation is now a method that iteratively computes these marginals by parsing messages between neighboring graphs. So basically it parses messages between syndromes and errors that basically are connected with each other. You start now parsing message around. There's a certain formula that you can derive. And just by the simple update rule, you can show that by running this update rule, you will find these corresponding margin probabilities. And you can now basically run this, find all the marginals. And then once you find the marginals, you can now do a simple mapping to what marginals into what error has occurred. In particular, if the probability of the particular margin is greater than half, to say an error has occurred, as to say no error has occurred. And you can basically prove that belief propagation works and converges to the true solution whenever the graph problem is a tree, meaning there's no loops. Loops mean basically that given starting from the node of the graph, there is no way to come back. Then it's loop free. And BP is for such tree graphs where there's no loops. It's known to converge exactly. Also known heuristically that if the loop is very large, it takes a long time basically to come back, then BP usually gives very good solutions. But if the loop is short, normally it doesn't work very well. And sadly, quantum error correction problems, decoding problems have lots of short loops, meaning BP doesn't work very well. And usually it won't converge. So if you just use the usual BP algorithm as usual, you find that it doesn't converge properly to the correct solution. That's why people propose to combine BP, belief propagation, with other methods. So there's something called order statistics decoding, which is just some post-processing method. And has been shown if you combine BP with OSD, you get relatively quite good performance. In particular, BP scales linearly and OSD scales cubically. And this has been heavily used in many papers and it works reasonably well. So it has been basically, and you can now compare the performance for this BP-OSD against Maxa, let's say. So we know BP-OSD is relatively fast, whereas Maxa is relatively slower, but we can now check the performance. Let's say for the color code. We can just look here at this graph here. We plot the physical error against the logical error. And let's say if you compare the green curve, which is distance 30 in color code for BP-OSD, against distance 30 for Maxat, we find that basically the green curve has a much higher error than the yellow curve, and also a different scaling. You can see the yellow curve for the Maxat decays much faster. So that basically implies that Maxat has relatively much lower errors than BP, OSD, and you can actually show that this corresponds to a decrease of a number of four times less qubits. So in other words, if we basically take a Maxat decoder on color code, then the error rate that we get with that corresponds to a BP OSD decoding, but with 4 times the number of qubits, like a distance which is much larger. So what I want to say is that just by choosing the right decoder, you can save a lot of physical resources simply by having a good decoder that can reduce errors by quite a lot and save you a lot of qubits, because then you need less qubits to get the same kind of error reduction. Yes, so you have to basically think very carefully what is the trade-off you can allow. Are you able to have more time, invest more time in decoding? Then you can use a decoder which runs faster but gives you better solution, better error suppression. But you can shorten time, yeah, you have to make sacrifices. So you always have to make this trade-off. Of course, BP-OSD is one method of many. People proposed recently many other variants of BP that seem to likely perform better than BP-OSD. So it's all an active matter of research. What is the best way to decode something? Okay. Another popular decoder is minimum weight perfect matching. Here, the idea is that you map the decoding problem onto a graph, right? So before, let's say you mapped it in a Maxat problem, or you mapped it into this kind of some structured graph problem. Here, you map it into a different kind of graph problem. So this graph is different than the one you saw for BP-OSD. Here, what you the idea is that what you do is you take your decoding problem and you map stabilizers onto the nodes of a graph, and the errors you map as edges onto the graph. Okay, so what it means basically, if you have a stabilizer measurement, each stabilizer corresponds to a particular node in this graph, and each error that can occur will correspond to some kind of edge. And let's say if we take the stabilizer, this particular stabilizer and this particular stabilizer, both stabilizers are triggered by the same error, which is given by this line here. Okay, and basically you can now map out a graph that basically then encapsulates your decoding problem. Now, of course, to write something in a graph structure, you make an assumption, namely that each error can trigger at most 2 syndromes, right? If let's say an error would trigger 3 syndromes, you can't write it as a graph anymore, right? Because it would be then a hypergraph. So in order to even make this mapping in the first place, you need to assume each error can trigger at most 2 errors, which is the case for some type of codes, let's say surface code, but not all of them. For example, color code doesn't have this structure. Okay, but let's assume we have now a decoding problem that somehow can be mapped onto this form here, where each error at most triggers 2 stabilizers. Then the perfect weight matching, what it does is you basically solve a particular graph problem. Is you have to basically, in this particular graph form, you choose the minimum number of, you basically try to color your graph. So you're trying to color the edges in different colors and basically trying to find a certain solution. In particular, you basically coloring edges and you're trying to find the minimum number of way of basically coloring the edges blue, such that blue edges interact with blue edges are incident on syndromes which are triggered with only an odd number of blue edges, whereas syndromes that have not been triggered or stabilized are incident on an even number of blue edges. Okay, so this is basically some kind of prescription how to color everything. To explain this maybe further, just look at an example. Let's say this is the decoding graph of the repetition code. So each node will correspond to basically some of these parity checks, and each basically edge in between would correspond to an error on a particular qubit, right? So if we now, let's say, assume that basically 2 syndromes were triggered, 2 stabilizers, which are colored as red here, then there's now 2 ways to solve this graph matching problem. So as we said before, we need that on nodes which are triggered, which are colored in red, only one, well, odd number, in this case 1, blue edge must be incident. So what we can do is we can simply draw color this edge here blue, this area here, edge here blue. Then we actually have what we need, basically because on the triggered nodes, only 1 blue edge is incident, right? So we're fine. In all the others, we can show only as 0 blue edges are incident, so an even number. The other way to color this problem would be basically to make the opposite. We color everything else blue, and this would also satisfy this problem, except this edge here, this edge here. So there's basically 2 possible descriptions, and the one with the minimum weight, with the minimum of blue ones, is this one here. So what does mean if we found this solution? This would mean basically that given this particular syndrome configuration, this error has been triggered. And this is actually also the correct solution with the maximum likelihood. Okay, so this kind of graph structure, graph problem solving is quite popular because there are very good classical algorithms that solve this graph problem in very short time. That's the famous Blossom algorithm that does this. So this is a very popular decoder that's been used widely in many instances, both in theory and experiment. Another type of decoder is the neural network decoder, where you basically take a completely different approach. You don't use an algorithmic approach, basically there's a particular prescription how you solve it. Instead, you just solve everything via learning. So basically, you generate a bunch of data, a bunch of errors, a bunch of syndromes, and you feed this into a giant neural network. In this case, it's something called a recurrent transformer network, but there's many different types. The one used by Google was a recurrent transformer network, which means there's some kind of memory. Basically feed in information, and the network pertains some information about what happened in the past. And this makes sense because normally error correction is done over many rounds, so this makes sense to retain information. And then basically you start training the neural network to basically try to find the optimal way to decode the problem. which you can do using simulated data, where basically you know whether an error or not has occurred. You can then just train the neural network and tell it, try to find the decoding such that the number of errors is minimized. And even finally, you can even put in some experimental data. And after training, they have shown that if you train this, it can show very nice performance. This is, for example, the red curve here, which is the result of the trained model, and it seemed to perform better than even the tensor network decoder. In this case, in this plot here, higher values means it's better. Okay, so it performs quite well. The downside is, of course, you have to train. So before you run it, you have to generate data and feed it into a network and start training, which can take a long time. And the scaling may also be unclear because for every new chip, right, you have to train again, right? Or for every different distance, for every different code, right, you have to do the training again. So these data-driven approaches basically require a lot of kind of initial work for training it, but once it's trained, they perform quite well. Okay, so besides these different approaches, there's many other approaches which I can't really explain because I don't have enough time. Just to give a very short overview, there's something called the tensor network decoders, which actually solve the full degenerate decoding problem by mapping them into a tensor network contraction problem. This is the best known decoder, I think, to my knowledge. But of course, its downside, of course, is we have the usual trade-off. It's very slow. Although recently people proposed to use belief propagation, in this term, belief propagation on the tensor network to find further speed-ups. So it's proposed by Itai and co. And a very nice work. There's also other types of decoder. Let's say a very popular one is Unifying, which is one of the fastest decoder out there. Something also called a tesseract decoder, which basically does some kind of search problems. Then there's also something called a renormalization group decoder, which basically is used for concatenated codes, where basically you solve each concatenation level of the code independently. So basically decode each concatenation level separately. And using this structure, you can find a very nice way to decode things. But there's many more, which go beyond SCONT, but there's nice reviews that basically explain all types of different decoders. So this is something you can check for yourself if you're interested. Okay, I just want to show you basically that the trade-off is something that's of speed versus time is something that's very real. In a recent paper, it has been studied basically what's the performance of the logical error rate for different types of decoders on experimental data. And they found pretty much what you expect from the runtime versus accuracy trade-off. For example, for the tensor network decoder, they found the lowest logical error rates for the experimental data. And then they basically found that, say, for faster decoders, like perfect rate matching, they found relatively, let's say, higher errors and so forth. So they found basically that basically there's this usual trade-off. If you want to decode something very accurately, you have to spend a lot of time. If you are fast, then you have to live with more errors. So this is a trade-off you have to basically play around with. Okay. For my final slide, I just want to give you some of these challenges in practice. So let's say you go away from theory and actually go into lab and try to think about how to actually implement quantum error correction in practice. You need to play with additional constraints. In particular, once you basically do the experiment, usually, if you want to run quantum algorithms, you need to decode while the quantum computer is running. Decode and correct while the quantum computer is running. So meaning this gives you a very string conditions, right? Because you have to consider, for example, let's say the gate time for superconducting qubits is, let's say, in the order of less than a microsecond. So meaning once you apply a noisy gate on the system, let's say some CNOT gate, you have then to do the correction operation, right? And you usually have to apply the correction operation before you do the next operation. So you have to be very quick, basically on the time scale of 1 microseconds. You basically have to be finished with all the process, meaning you need to do the full decoding process, including, let's say, readout of the synonyms, right, which takes some finite time. Then after you get the synonyms, you have to transfer them into, let's say, a decoding algorithm, which will probably sit on some kind of computer. But the question is, of course, where do you place the computer that does the decoding, right? Of course, let's say if you say, okay, I will just, let's say, get some kind of cluster, do the work for me that you put in some, let's say you do it on the cloud, right? And first of all, you have to send the data over the internet to a cloud, right? Now you can do the math, right? Let's say if your cluster sits 1 kilometer away from your computer, and if the information travels the speed of light, you already basically take 3 microseconds just to get the data there. So in other words, and this is already more than your gate time, right? You're already too slow. Meaning somehow so basically your computer needs to sit as close as possible to your quantum computer. Then of course your decoding algorithm needs to be fast enough, and then you also have to apply the correction operation. So everything, all these steps have to happen within, let's say for superconducting qubits, within 1 microsecond. If you basically use a different platform, let's say like N-traps, you have probably more time. But still, these are all short time scales. So basically, you have to think very carefully, basically, how you engineer all your whole systems, what kind of hardware to use. Use like specialized hardware that has like fast decoding rates, low latency times. You need to probably parallelize your decoding as much as possible, so you can run things in parallel. And particularly, you have to also keep an account in the future. Probably quantum computers will have 100,000 or millions of qubits, right? So as you scale up your quantum computer, of course, the decoding problem also gets more difficult. But let's say if your decoding problem now scales, right, gets slower as you scale up, this may already become then too slow, right? Because your gate times are independent of the number of qubits, right? So they've always been 1 microsecond, let's say. But if you scale up, the decoding problem, they become slower and slower. So even, let's say, if your decoding problem scales badly, let's say even maybe linear, may already be too slow for in practice if you go to a large enough number of qubits. So you have to think very carefully how you design and basically construct your system. So yeah, there's many things basically you have to consider. There's other things you may consider. Some decoders, for example, decoding time can also not be constant, but can also depend on the problem you have. For example, some types of decoders, not all of them, but some decoders, the decoding time, basically how long does it run, the decoder needs to basically spit out a solution, can increase with the number of errors that happen in your system or the number of syndromes that have been flipped. So this could, for example, could lead to a funny feedback loop where, let's say you have a certain number of errors, then let's say the number of errors increases, then basically the time you need to decode also increases, of course. Now, because you need more time to decode, you need more time basically to apply the correction operation, right? So basically, while your quantum computer is waiting for the decoder gives the answer, more errors have built up, right? Because just by basically waiting, you build up more errors, right? So since you waited now, more errors have happened, meaning the decoding gets even slower, right? So for these kind of decoders that basically like where the decoding time increases with the number of errors, you can be in trouble in this case. Okay, so these are basically many things you have to consider whenever you basically implement something. So decoding is a very, there's no clear-cut answer. That's my main point, how to do something. And depending on what system you have, what platform you have, what is your hardware, what you want to achieve, right? You may need to make different choices and basically play this trade-off and also play basically how you design your system, where you put your quantum algorithm and so forth, how you design your hardware. So you have to all consider these things together. Okay, so I think this encapsulates what I wanted to say for this session. And with this, I conclude basically the decoding session. And thank you much for your attention.
Thank you, Tobias. Any questions here from the audience? I think someone just typed in the chat box here.
Yeah, I see it. Local, yeah. Yeah, can you quantify? Yeah, I mean, there's asymptotic statements you can use. Sorry, I mean, the runtime of algorithm can usually be classified. For example, BP takes linear time. And so you have like often like worst case statements and say, let's say, effective weight matching also depends on the implementation one takes. So basically you can quantify what's the asymptotic time for a decoder to run, but often these are worst case statements, and on average you find maybe different numbers. The accuracy, this is something very difficult to theoretically evaluate. I think it's very difficult to say what's the theoretical performance of a decoder. So what people nowadays just use is going to just do numerics. Because different decoders behave very different depending on what kind of system you use. To give an example, let's say BPOSD, which I talked earlier, works very well, let's say, for toric codes, for service codes. But for color codes, it performs very badly. So you can't really generally say a decoder is good or a decoder is bad. It heavily depends on what kind of code you're using also. For example, in BPO, you have always issue that if the code has a short loops, then you're in trouble. So there's not a general statement you can make. You always have to basically trade off. So I think I'm not really aware of any good theoretical statements on the performance. And even for accuracy, usually we just have worst case statements, but not average case statements. So yeah, right now, what people do is using heuristics and just numerics. But yeah, finding good theoretical answers to this problem is very important, but I think so far not much has been done.
Yeah, Lorcan, you will see something soon.
Yeah, I have another question regarding the applications. So you mentioned that the minimum way perfect matching is only applies to like graph-like code, right? So like for the other decoders, are there any similar restrictions, or these are the universal decoders to any other kind of codes?
Yes, so minimum perfect matrix, as I said, only works on graph-like codes, but you can actually take any kind of graph, any decoding problem, and kind of approximately turn it into a graph-like structure. So you can always pick them apart and basically decompose errors. So basically, if you use stim, which I talked earlier, right? Stim does it automatically for you. It will already find that you can feed in any type of decoding problem, and it will just then approximate using graphs. Because stim uses perfect weight matching usually. The other decoders are universal to some sense. For example, BP doesn't have this constraint, let's say, on the problem doesn't need to have a graph structure. You can also you can decode arbitrary parity check matrices. But again, not every, but you can have more complex decoding problems where you have like correlated errors. So basically, right now everything here we assume the errors are uncorrelated, but you can also have basically instances where suddenly errors start to correlate with each other. So for example, here neural network decoders perform very well. Can you see it? Yeah, so basically this is one of the reasons why neural network decoders performs well, because they deal very well with correlated errors that happen. They basically feed in like exponential data that basically show them instances of these kind of correlated error. Basically, errors have like the correlations between different, so errors are not independent, but show some correlated behavior. And basically then we manage to decode this better. And I'm not sure if this can be easily captured using the standard parity check matrix. Also, like one thing important is to consider that usually when we have CSS codes, we decode X errors and Z errors separately. Right. If you remember, like we have like in CSS code, we have like X and Z matching, they're kind of independent. So the assumption is basically that you can decode X and Z separately. But this is actually an approximation, and this will introduce some errors because Y errors are actually correlated. Because if an Y error happens, there's an error both in X and the Z part. But if you decode them separately, you assume basically that the X, that they are independent. So you could also basically correlate these Y errors in a proper way, then you basically have to solve a more complicated problem. Which I'm not sure can be captured by usual methods, like BPO. Most team may not be able to capture this, I think. But there's other methods that can solve such problems. So yeah, so I think once you go to correlations, like error correlate errors, you have to think more carefully. I'm not sure if all decoders can do that.
Thank you, Toby. Okay, so if there isn't any question here, so we end here today. Okay, thank you everyone. Thank you, Toby. It's a very nice talk. Okay, see you guys next week.
Bye.
Thank you.